All right, good afternoon. Let's start our lecture today. In our previous lecture, we have discussed about motion in one dimension. We have studied the kinematics equation in one dimension. We have studied kinematics in one dimension. Now we are going to extend our study to higher dimensions. But before that, we have to learn the language of vectors. Because in order to express the position of an object in two-dimensional or three-dimensional space, we have to use the language of vectors. I think some of you might have learned vectors in your high school physics and your high school mathematics, the extension part, but we still have to go through a more thorough study of vectors, and I will introduce to you some of the conceptual subtleties of the dot product and also the cross product, and how they are applied to a physical situation to describe the motion of a body. So let's have a review and also some new things, learn some new things about vectors. Now, we also would introduce to you the coordinate system, the curvilinear coordinate system that we commonly used in our study of physics. Okay, so this mathematical review is vectors and coordinates. Now, first talk about vectors. Now, the elementary definitions of vectors and scalars are that the scalars are physical quantity with magnitude only. So it describes how large and how small the quantity is. It does not have a direction. But for vectors, you have both. This is a physical quantities with both magnitude and direction. Okay, so a vector is a quantity with direction. And how to represent the vectors? We usually represent the vectors by an arrow with a certain length. And the length of that arrow will represent the magnitude. Given a certain scale, for example, if this is a force, then you may represent a Newton of force by an arrow of length 1 cm. So if you have a force of 10 Newton, that will translate to 10 arrow of 10 cm in length. So you require a scale to convert the quantity that you want to describe into the length of that vector. Okay, and the arrowhead, of course, denotes the directions of the vectors. And in books, the vectors are denoted by a bold-faced letter. But when we write the letter, when we handwrite it, it's not that convenient to use a bold-faced letter, and so we usually write a small arrow above the letter to denote that this is a vector. And the magnitude of the vector is denoted by its absolute sign that denotes the length or the magnitude of the vectors. And in this course, we simplify the notation. The mathematicians may become more rigorous in the notations. They may use an absolute sign or even the modulus with a double vertical bar. But in this course, we want to make the symbol simpler. So we simply use A without the arrow sign to denote the magnitude of the vector A. So A with the vector sign denotes the vector itself, and A without the vector sign denotes the magnitude of that vector. And the negative of this vector of a vector is defined as that vector, but within the opposite direction. So this is vector A, and this is vector minus A. Okay, so we simply reverse the direction to get the minus of a vector or negative of a vector. Now we add two vectors by the tip to tail methods. Each vector has a tip and a tail. So if I'm given two vectors, I connect the tail of one vector with the tip of the other. And then the resultant or the additions the additional result of those two vectors from the tail of the first vector to the tip of the second vector. Okay, so this is the resultant vector C. Or equivalency, we can describe this additional method by using the parallelogram. Okay, for the parallelogram method, we first drawn the tail of the two vectors together. Okay, and we draw two parallel lines, two lines parallel to the two vectors, such that the vectors together with this two dashed line, they form a parallelogram. And the resultant vectors will be the diagonal of this parallelogram. Now you can easily see that if I move the vector B to the opposite side here, it is just equivalent to the tip to tail method. So both of the methods are just equivalent to each other. So it depends on in what situation you are dealing with and with what methods that you feel more convenient. Okay. Now, and then we can also define this subtraction of two vectors. Okay, we have if I have two vectors A and B, I add A and B. We can do it with the tip to tail method. But now, how about A minus B? How to do that? Now, the idea is easy. Because minus B is defined as a vector B with the direction in reverse. So this is the B vector, right? And minus B is the same vector, but with the direction reverse. So A minus B is just A plus the vector minus B. So this is the vector minus B, and this is the vector A. And so I just add them up to get the resultant. The resultant will be given by this diagonal. Okay, so you can see in this parallelogram, A plus B give you A plus B is expressed as one of the diagonal of the parallelogram, and A minus B is expressed in terms of the other diagonal. Okay. For me, it may be more convenient to memorize instead of turning the B in the reverse direction and then add to A. For me, it will be more convenient to memorize the subtraction of two vectors in this way. I draw the tail of the two vectors together. So this is A and this is B. And I just memorize like this. The vector subtraction A minus B is just a vector that goes from the tip of B to the tip of A. So A minus B give you a vector that goes from the tip of B to the tip of A. I memorized it like this. So it depends on how you find it convenient. There's no absolute method, correct or wrong method to memorize it. It just depends on the matter of convenience for you. So you just do it in your own way. As long as it's correct, then it should be okay. And if I have A minus A, then of course the vector is 0. I usually here I use a vector sign above the 0 to denote that it is vector. But in most of the situation we skip this vector sign. A minus A simply is 0. Okay. Now what we have introduced is a graphical method of adding two vectors. But the graphical method is not that convenient to do in terms of the calculation. So we prefer to do it by using the components. And we introduce a new method called algebraic method, which make use of the components of the vectors. Now, this is a Cartesian coordinate. I suppose the vectors are now on the XY plane. So I can resolve a vector in X direction and in Y direction. Okay. And AX, which is the projection of the vector A onto the X-axis, is called the X component of the vector. And the projection of the vector A onto the Y-axis that give you AY is called the component of the vector in the Y direction. So the component are the scalar. Okay, there are two numbers that specify the projection of the vector on the x-axis and the y-axis respectively. Okay, and I think you know, if I would like to express the components in terms of the length of the original vector, the magnitude of the original vector, and also the angle that it makes with the x-axis. And from this triangle, this is a right angle triangle, you can easily see that AX, the X component is just A cosine theta, while the Y component is just AY, is just A sine theta. Okay. And conversely, if you are given the components AX and AY, you can also find the magnitude and the angle. That is, of course, given by the Pythagoras theorem because this is right angle triangle. So A is equal to A squared plus AY squared square root. And the angle theta is given by arctangent of AY divided by AX. Okay. Now, but be careful. In this figure, I draw the vector A in the first quadrant. But imagine now the vector A can be at any point in XY plane. So you must be careful in determining the angle theta. Suppose the angle theta is positive. You find it to be positive. You use a calculator and you find it to be positive. Must it be in the first quadrant? You might want to ask this question, right? Now I would say something like this. If you find both AX and AY are positive, if you find both components of the A are positive, then the angle theta will be in the first quadrant. So you can usually do it, calculate the angle theta by using a calculator, right? However, if both AX and AY are negative, so that means in what quadrant that the vectors are in. If both AY and AX are both negative, that means the vector is in the third quadrant, is somewhere here, right? So can you now simply use your calculator to find the angle theta? No, because you will got an angle in the first quadrant. AY over AX is still positive, but obviously the vector is not in the first quadrant now, right? But it is in the third quadrant. So a better way to do this is to take the absolute magnitude of both AX and AY. You'll find the complementary angle first, and then if it is say in the third quadrant, then you just find it by subtracting the angle by 180 degrees. Now, in order to make it clearly, I better write on here. Now, suppose a certain situation is that you find both AX and AY smaller than 0. So sorry, I better use my eraser. Suppose the vector is in the third quadrant. Okay, so in this case, this is the angle. This is the angle theta, right? It is not this angle, and you will find that if you are given two components, you will find that both AX and AY, they are smaller than 0. Is that right? So how do you find the angle theta? Now the idea is that you first find the complementary angle first. The complementary angle is this angle, the acute angle that it makes with the x-axis. So this formula, it does not directly give you the angle theta, but it gives you the complementary angle. You take the absolute sine of AY, and you take the absolute sine of AX, you divide AY with AX, and you take the arctangent. you get the angle alpha, right? And in order to get the angle theta, you just add what? You just add the 180 degree, or in terms of radian, that is pi. You just add pi to alpha. So that is a way to do it. Now, the angle may be, in other cases, the angle may be in the second quadrant where AY is positive, but AX is negative, or in the fourth quadrant where AX is positive, but AY is negative. Now, so you should be aware of these cases, okay? And in that cases, you should be able to find the complementary angle first, just like this, or you can subtract it with 180 degree in the second quadrant, or you can subtract it with 360 degree in the fourth quadrant. Okay, so in this way you can find the correct angle. Okay, I don't discuss with you case by case. I think you know how to do it, but I just want to remind you that you have to take care of these special cases. Okay. Now with the components, you can add up two vectors algebraically, because the components are numbers, right? So they can be added algebraically. Suppose we have the vector A and the vector B. We do it. We solve the components. So the component of A is AX. The component of B along the x-axis is BX. Okay, so AX and BX are the components of the vector A and B along the x-axis. And this is the resultant C, right? The sum of A and B. And if I resolve the vector C along the x-axis, I also got this, the x component Cx. And you can easily see from this diagram that Cx is simply Ax plus Bx. Okay, and you can do the same thing for the y direction. And you can easily find that Cy is Ay plus By. So that's why we can add the component separately. In order to find the component, x component of the resultant, you simply add up the x component of the two vectors. To find the y component, you simply add up the y component of the two vectors. And this can actually be generalized into 3 dimensions. If you are now talking about vector in 3 dimensions, you have the z component, right? And so the z component Cz is given by Az plus Bz. Okay, so this is easy. You just add up the components of the individual vectors to get the components, corresponding components of the resultant. Okay, and similarly for subtraction, for Cx, you have Ax minus Bx. For Cy, you have Ay minus By. Okay, now although I draw the vectors such that both A and Ax and Bx are positive, if one of the vectors or one of the two vectors have a negative x component, the relation still hold. Okay, it only that if, for example, if Bx is negative, then it points to the opposite direction, point to that direction, and this will become a minus, the difference between the two vectors, but the relationship will still hold. Okay. Now we will introduce to you the language of basis vector. We probably will like to express our vector in terms of the basis vector. The basis vector has vectors of unit length. The magnitude is by definition 1. And in 3 dimensions, we denote the basis vector ijk. Ijk are the unit vector along the x direction, y direction, and z direction respectively. So in this diagram with only 2 dimensions, I have only I vector and j vector, and the magnitude of the vectors are both equal to 1. Okay. Now, so a special notation here. I have a hat, right? I put a hat above the symbol. If you see that I put a hat above a symbol, I always means that that is a unit vector. So that means that vector, that is a vector, but with a magnitude equal to 1. Okay. Now, so in terms of this basis vector, I can write the original vector in terms of the component. Okay. This is the original vector A. And of course, I can see if I adhere a basis vector I to the component AX, I have this horizontal vector. If I adhere the jade unit vector with a component AY, I have this vector, right? And obviously, AXI plus AYJ give you the original vector. Is that right? So now I can write the original vector as a sum of two vectors. The first vector is being in the x direction, and the y component and the second vector being in the y direction. And the magnitude of these two vectors are, of course, the component of the original vector in the two directions. So they are ax and ay. Okay, and similarly for the other for another vector, I can write as bxi plus byj. This is the vector b. Okay. Now, if I want to add two vectors together, okay, I can do it algebraically. That is very convenient. I can treat the unit vector I and the unit vector j just like they are separate variable. And so when I add up two vectors, I just gather the term with the unit vector I. So this becomes ax plus bx multiplied by I. And I also gather the term with the unit vector j. So it becomes ay plus by unit vector j. And so you can easily see that the x component of the resultant is just ax plus bx, and the y component of the resultant is just ay plus by. Okay. Now the algebraic method can be easily generalized to 3 dimensions. That means if you have the z component, then there will be a very straightforward generalization with a z component of a k with a k vector. And the algebraic method also allows you to handle a very complicated situation, and that is very exact and precise. It's different from a drawing on a graph paper. It's not rely on that. It is very precise because you can add it up using your pencil and paper and also your computer. If you are given 100 vectors, for example, you can actually write a program to add up all those vectors. So this is a very systematic and robust way to add up those vectors. So this is a straightforward generalization. We have the Z component now. So this is a 3-dimensional space. Okay. I just give you a break so that you can have a review of what you have learned. We have 2 vectors here. Why not add up these 2 vectors? And I want the magnitude and also the angle that the resultant make with the blue dashed line. So I want you to find the resultant, the magnitude of the resultant, and the direction, the angle that the resultant makes with the blue line. Okay. So I give you 5 minutes to do it. You can do it with whatever method you like. So what do I have? I have 2 vectors now, right? The 2 vectors are given by like this, 100. This is 30 degree. And I also have a vector of 200. These are the displacement. That makes an angle of 60 degree with a certain direction, right? So I can write this vector as A. And A is, what is the x component of A? If I call this direction x, then I will have 100 cosine 30 degree, right? I direction plus 100 sine 30 degree in a j direction. And similarly, for this vector, I call this vector b. I can also write the vector b in terms of its component. For those who have a knowledge of trigonometry, you may be able to convert this cosine, because this is a special angle, right? So you may be like to convert this number, this sine cosine into short form, okay? But I'm not that interested in doing this detail. I simply add up the two. So a plus b is what? You may like extracting a factor of like this, I plus, you may extract a factor of 100 also, sine 30 degree plus 2 sine, sorry, this is 60, I write wrong. As I say, if you want to answer to be very nice, then you can convert the cosine 30 degree is square root 3 over 2, and cosine 60 degree is just 1/2, right? And you have for this sine 30 degrees 1/2, and sine 60 degree is square root 3 over 2. So you now have square root 3 square root 2 over 2 plus 1 I plus 100 again. Against we have a square root 3 plus 1/2 j. Okay. Now this is your cx and this is your cy. If you want to find that angle, you can easily take the arctangent of cy over cx. Okay, you use a calculator to find that result. And if you like, you can also calculate the resultant, the magnitude of the resultant. This c is cx squared plus cy squared square root. Okay, I don't proceed with the calculation. You can do it yourself at home, or you can use a calculator to find the result. Okay. I share with you the screen, so you can have your review. I go back to my PowerPoint again. So before having a break, I want to talk a little bit about the curvilinear coordinate system. Now this is something maybe something new to you, and sometimes it may be quite complicated. Now first we talk about polar coordinates. Now in fact we have already encountered polar coordinate before. A point on the xy plane, it may be expressed in terms of the x coordinate and the y coordinate like this, xy. But it can also be expressed in terms of a distance and an angle. The distance r is the distance of that point from the origin. I denote this distance by r, and the line joining the point with the origin makes an angle theta with the x-axis. And so I define the theta like this. And so the point is now expressed in terms of r theta, and that is called polar coordinates. Okay, polar coordinates. And you can easily see that just like the resolution of the component, the x and y coordinates is related to r and theta by x equal to r cosine theta and y equal to r sine theta. And conversely, if you are given x and y, you can easily convert it into polar coordinate. It is just like finding the magnitude and direction of a vector from their components. If you are given two components, in fact, x and y are just a component of the vector r, right? So if you are given the component x and y, you can use Pythagoras theorem x squared plus y squared square root to find the magnitude of this length r. Okay, you can imagine that this to be a vector. Okay, and again, the angle theta that's this length mixed with the x-axis can be found by arctangent 1 over x. Again, you should be careful if the angle is not in the first quadrant. Okay, in that case, you have to find a complementary angle first, and you may need to subtract or add to 180 degree to get the final answer. Now, sometimes we use polar coordinate instead of Cartesian coordinate to describe certain motion. For example, imagine now if you have a circular motion. A circular motion obviously has a constant radius, right? The distance between the points from the center of the circle remains constant. So one of the coordinates in polar coordinates is a constant. And the angle theta is either increasing or decreasing with time. It's described by a function in time. So we write theta as a function of time. So in that case, the circular motion can be more conveniently described by the polar coordinate than the Cartesian coordinate. So when we talk about circular motion, we prefer to use the polar coordinate because r is a constant. That simplifies things a lot. If you use a Cartesian coordinate, then you can see from this expression, the x will change with the angle as cosine theta, and the y will change with the angle sine with the argument sine theta, and that will be very complicated. Okay, so that's why changing a coordinate allows us to describe a circular motion in as much a simpler way. Now, the so-called cylindrical coordinate is a straightforward generalization to the polar coordinate. We simply add the z component. Okay. Now, this is a general point. I will answer your question later. Okay. Somebody asked me, is physicists using r and theta to denote a vector in terms of x and y? Yes, you can imagine this to be a vector. Okay, you can actually write this vector as r vector like this. You can actually write this as a vector. Okay, so if this is a vector, then the x component of this vector is x, and the y component of the vector is y. Okay. So that is also a commonly used way to express the position of an object. Now, a cylindrical coordinate, as I say, is a straightforward generalization to the polar coordinate. We just add the z component. Now this point is in three-dimensional space. It is not on the xy plane, but it's different from our previous discussion only by a certain height above the xy plane, right? So we just use another coordinate, that is the z coordinate, to describe the heights. Okay, so we have the z coordinate here, and when I project this point on the xy plane, I can resolve that this point into x and y component just like what we did for the polar coordinate system. So so the x and y component are just following what we have for the polar coordinates. The length r is the distance of the point from the z-axis. So this length r is the same as this length r. So the x coordinate is r cosine theta, while the y coordinate is r sine theta. And the z coordinate is simply the height of this point above the xy plane. Okay, it's just the same as Cartesian coordinate. Okay, So now we have a complete transformation from the cylindrical coordinate, which consists of the distance r from the z-axis, the angle that this projection point makes with the x-axis, that is theta, and also the heights, which is described as ez. Okay, so that completes the transformation. Okay, and you can see this is a simple generalization of the polar coordinate to 3 dimensions. We just add the ez component. Okay, and also the inverse transformation is the same as polar coordinate. The ez is the ez. This doesn't change. You can just use x squared y squared square root to find r and arctangent y of x to find theta. Okay. Now, a word of note is that usually when we count the angle that this line makes with the x-axis, the range of the angle goes from 0 to 2 pi. Okay, so it goes around in a circle. Okay, and sometimes people may like to denote it with minus pi to pi. That is equally okay. But this is a general, more general way to describe it. We usually have the range of theta extend from 0 to 2 pi over in a full circle. Now we can also express a point in 3D space by the so-called spherical coordinates. Now this is a rather confusing symbol that you might dislike, especially the mathematician. They ask me why I use the symbol r for the distance between the point and the z-axis in cylindrical coordinate, and now I am using the same symbol r that denotes the distance of the point from the coordinate origin. Now the reason is that people are using cylindrical coordinate and spherical coordinate a lot, and they use the same. Actually, they use the same symbol, especially the physicists. And so I prefer not to introduce another symbol for you, because those other symbols, like for example, some people like to use rho for this distance, but rho, the symbol rho, is actually used at the density, the charge density in electromagnetism. So I prefer not to use an extra symbol. But instead, we should specify very clearly what kind of coordinate that we use. If you are using spherical coordinates, then the distance r refer to the distance between this point and the origin. If you use cylindrical coordinate, then the distance r refer to the distance between the point and the z-axis. Okay, so they are different. Okay, so now we are at the spherical coordinate, so we have this distance r from the origin, and also we have two angles. The angle theta is the angle that this line, that the line joining the point and the origin, makes with the z-axis. This angle is theta. Okay, so this is the z-axis. This is the line joining the point and the origin. The angle between them is called theta. Okay, and again, I can make a projection of this point onto the xy plane, and I draw this line. I draw this point to the origin, and this line make an angle phi with the x-axis. So that defines another angle phi, which I call azimuthal angle. Okay. Now, the angle theta defined here is not the same as the angle theta here. So there's a little bit of confusion. But as long as you specify clearly that you are using the spherical coordinate, that should be fine. We define the angle theta as a polar angle because that is commonly used in physics literature. You see all the advanced physics textbook, including those in mechanics, those in quantum mechanics, and those is even in quantum field theory. They use general relativity. They use the angle theta as the polar angle, the angle that the point makes with the z-axis, and the phi always refer to the azimuthal angle. This may be different from some of the mathematicians' definition, but physicists always use the angle theta and phi this way in the spherical coordinate. So I better keep this convention in order for you to be to accustom to it and be able to use the same symbol when you are studying in a senior level course. Now, how about the transformation? The transformation get a little bit difficult, but it's not that scary. Now you can see if this is R, this angle is theta, then the distance between the point and the z-axis is R sine theta, right? Because this triangle is a right angle triangle with a right angle here. So the distance between the point and the z-axis is R sine theta, which is the same as this line, right? The projection line is also has a length of R sine theta. So if I project this line R sine theta onto the x-axis, where I get the x coordinates, I get the extra factor of cosine phi, right? So I have R sine theta of this line multiplied by cosine phi will give me the x component. And if I have R sine phi and if I have R sine theta and I multiply and it with sine phi, then I get this length, which is the y component. So I got the x component and the y component like this. The x component is R sine theta cosine phi. The y component is R sine theta sine phi. If I want to, the z component is simply R cosine theta. So I got a three component x, y, z component in terms of R theta and phi. The reverse transformation is also simple. I just apply the Pythagorean theorem twice to get R. R is x squared plus y squared plus z squared square root. And the angle theta is arc cosine z, which is this height, divided by R, right? Theta is arc cosine z divided by R. And this angle phi is just arc tangent y over x, right? Okay, so that completes our transformation. Now, a word of note is that the angle phi, the azimuthal angle, it extends around the z-axis in a full circle. So it goes from 0 to 2 pi. It goes around in a full circle. But the polar angle theta is not that is the definition. The range definition is not from 0 to 2 pi. It goes only from 0 to pi. When the angle theta is 0, that means the point is on the positive z-axis. When the angle theta is, say, pi over 2, that is 90 degrees, then the point is on the xy plane. And if the angle theta is pi or 180 degrees, then you can see when this angle is 180 degrees, the point is actually on the negative z-axis. Okay, so if the point goes to the other side, I prefer not to use the angle theta to define it. I prefer use the angle phi to move it to the other side. So the angle theta is defined from 0 to pi only. It cannot be larger than pi. While the angle phi goes around the z-axis in a full circle from 0 to 2 pi. Okay, it's okay. Now, although the spherical coordinate looks a little bit clumsy, a little bit difficult, we are using it every day when we described the coordinates of a certain place on Earth. We use the latitude and the longitude to describe the position of the place on Earth, right? But that is exactly the spherical coordinates. In this case, we assume the Earth to be a perfect sphere, so the radius of the Earth is a fixed, okay, and the latitude is actually the polar angle theta, the complementary angle to the polar angle theta. The equator is defined as a 0 degree latitude, and if you are living in a place that makes an angle 30 degree with the equator, then you are at 30 degree north in latitude. This is a line of 60 degree north in latitude, and you are at the North Pole, then you have the 90 degree north in the latitude. Okay, so the latitude on the northern hemisphere is defined by the positive value, while the latitude in the southern hemisphere For example, this line is defined by a negative value. So the longitude is a great circle joining the North Pole, then South Pole, and that place. And the longitude is defined as the angle between this great circle and another great circle that join the North Pole, South Pole, and Greenwich. So by definition, Greenwich has a zero degree longitude. Okay, and a place that is east of Greenwich is defined to have a positive longitude, while a place that is west of Greenwich is defined to have a negative longitude. Okay, so that's how we define latitude and longitude. And you can easily see that what we call latitude, if I define the axis pointing to the North Pole, is the Z axis. Then this angle will be theta in what? In spherical coordinates, right? And this angle is latitude, right? So the theta and delta, the latitude, they are the complementary angle. So you only need to subtract 90 degree by delta by latitude of that place to get the polar angle theta. Okay, if the North Pole is defined along the positive Z axis. Okay, and in that case, delta essentially extend from negative 90 degree to 90 degrees. So you got the angle theta extend from 0 to 180 degree. And the angle phi is just the longitude. In spherical coordinate, the angle phi is just a longitude. And in this special case, we don't have a 0 to 2 pi. We have a phi extend from minus 100 degree to plus 180 degree. Okay, that is a convention for longitude only. Okay. Now, so if you are given you are given the latitude and the longitude of Hong Kong, so you can easily convert it into a spherical coordinate. You know the radius of the mean radius of the Earth is 6,370 kilometers, so that is fixed. Okay, and you can find the polar angle by subtracting the latitude by 90 degrees. So that is the polar angle, and the longitude gives you the azimuthal angle phi, 140 degrees. So you just plug in this angle and the radius of the Earth into that standard transformation, and you will be able to get the XYZ coordinates, okay, of Hong Kong. Okay, so that is referring you to a particular Cartesian coordinate system. Now I better have a break here. This is a long lecture.